Gauss's law is a means to an ends. And what I mean by that is it's a great law, but for the most part, it is useless. And quite literally useless. And here's where I need to be very intentional about how Gauss's law actually works. As a mathematical expression goes, it is very unlikely that you will be able to actually act on this integral. I know. Just wanted to get it started. God, you guys are so mean to me. This is why I don't want to answer any questions over the weekend. I just want not to know that you guys exist. So it is very unlikely that you'll be able to act on this integral. Because no matter what, for those of you who are just now, getting into calculus, one of the things that is missing is the only way you can act on this integral is if you have an expression for the electric field as a function of the area. And that's unlikely to exist anywhere. I mean, for one, we don't typically have expressions that are in terms of area. We might have expressions that are in terms of positions that you could eventually turn into an area, but for it to be in 3 dimensions suggests a lot of difficulty in your actual computation, because this would actually mean, and I'm just putting this up here just to see if I can, have you understand the difficulty we actually have here, is you would have to do 3 integrals, not 1. 1 for every direction. And since it's likely that these are all related, then you would actually have to do this as a simultaneous triple integral, which is actually a thing. Except you also must, and this is where it becomes difficult, you must employ the dot product, which means we don't also have to do this evaluation, but we have to take into account at every point in space where there's a piece of area, the direction of the electric field relative to that area. There's a whole new mathematics created just to do this, in figuring out this kind of vector field displacement in space. Which is why we can't. We shan't do this. What we use Gauss's law for instead is we use it in situations where either A, we are interested in the enclosed charge only, or B, we can exploit some feature of the symmetry. Those are the only opportunities for us to use it. Which is why, actually, for Gauss's law, we can only use it in about 3 or 4 circumstances. Look, I know that this is disappointing in some cases because I've said this before where, look, this is what we have for physics, but you can never use it because you can't do any of the math for it. But unfortunately, in the beginning of the year, before we get to circuits, there is a lot of that has to go on. Because field theory is a little bit challenging, and even a very competent calculus student will have not covered some of the math necessary to do some of the work that we're suggesting has to be done here. Remember, physics created this math to solve these problems. And the problems got more complicated, so more math had to be created. So when we talk about Gauss's law, we're really going to be talking about it in a very generic sense, as a means of solving some specific problems, but also to give us a qualitative understanding of what might be happening in the universe. So in order for me to convey this to you, I do want to look at 3 specific circumstances. And the very first circumstance I want to look at is the point charge circumstance. Because if nothing else, the point charge offers us kind of a symbolic representation of how to use Gauss's law. So we're going to have a single point charge in space labeled capital Q. Just a single point charge in space. I would like to use Gauss's law to determine the electric field from this point charge. Something to which we already know the answer. But the point here isn't about the answer. It's about to demonstrate how Gauss's law can be used to produce the answer. And this is because of three potentially more complicated circumstances. One, we can extrapolate this from a point charge to a solid sphere of charge, or for like a gaseous distribution of charge, something that actually exists in the universe, like a star or a nebula or a planet. So there is practical application there. Second, the point charge helps reinforce Coulomb's law. So to do this, I want to remind you of how we use Gauss's law. And what I'm doing here is I'm transitioning from what Gauss's law is actually about to a specific set of steps for how to use Gauss's law, which I guarantee you is on the exam. More importantly, this is the kind of problem I put on your first test, which I've already written, by the way. So the first thing you do in dealing with the Gauss's law problem is you attempt to find an area that exploits symmetry. Now, let me be very clear about what this is going to be. You're looking for a shape or a surface where the electric field is known or can be surmised by the shape. So on Friday, I talked about the fact that I would not wrap a cube around this, because a cube would have differing electric fields at every point on the surface of the cube. Instead, I would find something that has symmetry. And so you all likely surmise that probably the best surface to use would have been a sphere. And that's what we're going to use, a sphere. And we're going to be careful to try and place the sphere so that it's concentric with the charge. The reason is because that would suggest then that every point on the surface of this sphere is the same distance away from the charge. So choose a surface. You can surmise the electric field. Now, I don't need to know what the electric field is. I just have to be able to surmise some properties of it. 2, once you've done that, you want to compute the flux. There are several things that we're going to try and do to compute the flux. And I want to remind you that the flux is made up of 3 equally weighted pieces of information. There is the size of the electric field at every point on the surface. There is the size of each individual piece of area that comprises the surface. And there's a computation to determine how much of the electric field is aligned with the surface for every piece of surface. Now, I can't write all of that on the paper. I'm hoping you are, and I'll say all 3 of those again. The first thing there's 3 parts to the flux. There is the size of the electric field. How much electric field is piercing the surface? There's the size of each individual piece of area that comprises the surface. And then there's a final computation to tell us how much of the electric field is in the direction of the surface. Now, we're trying to dissolve the integral, is what we're really trying to do. We're trying to find a way to get rid of the integral. So we're trying to see if the symmetry we've chosen can help us with this. And here's part of that argument. By making the sphere concentric, I've purposely made sure that every piece of area is located the same distance away from the center. Now, the goal for this was to try and make it so that the electric field is likely the same at every point on the sphere. Is there any reason not to believe that? That the electric field is the same every point away from the central charge? So if we can state that the electric field is the same, it's a constant. Now you guys, this might be something that's a little beyond your experience, but when we did the antiderivative in mechanics, did you notice that constants just kind of don't do anything? They just stay there? It's the same in this class. Everything we're trying to do here is about creating the antiderivative. If E is a constant, then mathematically it can pass outside of the integral. Because what's left is for me to find the antiderivative of the area. However, I can't do that yet, technically, because I never dealt with direction, which is the next question you should ask before you pass that outside. And the electric field has got to be in this direction, right? By definition, it's away from the positive charge. So the real question is, how would that be related to the direction of the area at that point? But it's a sphere. Wouldn't the area at that point have to be in the same direction? It has to be perpendicular to the surface. And perpendicular to the surface lies along a radius. And this is a radius. Now look, you have to be able to make this argument. And none of the things we've talked about here yet are outside of your mathematical skill. But you have to make this argument each time you're given a surface. So right now, what I've done is I've been able to take that dot product and turn it into a cosine of 0 degrees. Because I've demonstrated that the electric field is in the same direction as the area for every point on the sphere. And although I didn't say it that way, does it change if I go over to this point? Won't this radius now point in a new direction for that area, but won't the electric field also be in this direction? Can we use symmetry to state that that's true for every piece of area? And if we can, then we can turn the dot product into cosine 0 degrees, which means I am now left with this as my integral. That's our goal, is to try and weed down the expression for the flux until we get just this. Because although you don't know it yet, all this says is to add up the entire area of the surface, which just means it's the surface area of your shape. That's all that integral is telling you to do. Sum up every piece of area for an entire enclosed area. What's the surface area of a sphere? 4/3 pi r cubed is actually the volume of a sphere. So surface area of a sphere is? Oh, wow. So you're saying you don't know? Yeah. Okay. That's fine. That's fine. Surface area of a sphere, committed to memory, 4 pi r cubed. I can see it just fine. Wow. So let me throw a few things out there since I'm hearing some confusion. First, it's an area, so it's always going to be squared. Cubed would be a volume. That's not an accident. Keep that in mind. If you work something out and it's supposed to be an area and you get something about the shape cubed, you've done it wrong. It's going to be something about the shape squared. That's an area. That's what produces the meter squared part. Second, yeah, that is the equation for a surface area of a sphere, 4 pi r squared. All right? Can I go on? I need to, because we have now computed the flux portion, which brings us to step 3. And I'm kind of out of space here, so I'm going to move these other steps off screen. So, step 3 is to use Gauss's law. Q enclosed equals epsilon naught times the flux. Now, our Q enclosed was just Q, the charge at the center. If I'm hoping to use Gauss's law to figure out what the expression for the electric field is, then I just want to solve for E, the electric field. Now, I solved for E, but I collected all of this together. And I did so on purpose because everything that's there is a constant. Right? Go ahead. Well, that's what I was going to say, but you stole my thunder, so it's okay. But I'm glad that Max brought it up. If you read the textbook too, you might know that. But more importantly, that's exactly what I was trying to get at. That this is the expression we were already expecting. It's Coulomb's law. The only difference is that we just wrote K as our constant. Now, Coulomb didn't know that there was this other more important value known as the permittivity constant. That wasn't part of what he knew. But today we recognize that Coulomb's constant is actually a collection of other things. And it's kind of interesting, the things that have appeared here. One of the themes you're going to see in class all year long is that pi is a part of the fabric of electronics. I mean, you are seeing it here, right, for the first time, where pi shows up as the electric field around a point charge. We're going to see it all over the place. For whatever reason, because of the circular nature of the electric field, pi is a part of the fabric of space. And 4 pi shows up more consistently than anything else. And it's all because of the spherical nature of the electric field. So if you get an answer that doesn't have pi in it, that should be a warning sign that you might have done something wrong. Because almost every answer we get here is going to have a pi in it somewhere. Next, this allows us to transition. We are not going to use 9 times 10 to the 9th anymore. Newtons meter squared per Coulomb squared. We're not going to use that hardly at all. You'll be expected to use epsilon naught because it shows up in other places. And that's pretty low on the board for you guys to see, but let's now flesh that out because I did not do this before. Epsilon naught is 8.85 times 10 to the negative 12th Coulomb squared per Newton meter squared. That is the permittivity constant. Its units are just the inversion of the units of K, but the value is 8.85 times 10 to the negative 12th. Yeah, I know, it was easier to remember 9 times 10 to the 9th. But we use this in other places too. Now, a problem known as the infinite line. infinite line of charge. An infinite line of charge is exactly what it sounds like. It is an improbable circumstance, but it is an infinite line of charge. An infinite line of charge would not have an amount of charge. An infinite line of charge would simply have a charge density. So we're going to say that our infinite line of charge has charge density lambda, because that is the charge per unit length. Now, there are no infinite lines of charge, but there are lines of charge that you can get very close to and act like infinite lines of charge. So any problem that has something that says it's infinite is because there is a finite version of it that actually is applicable to the problem. So there's not many, incredibly long lengths of charge, but there are wires. And wires to an electron look infinitely long. We're going to talk about, infinite areas of charge or infinite sheets of charge. There are no infinite sheets of charge. But a large piece of aluminum foil looks infinite to an electron. So that's why we look at the infinite case. Also, the infinite case lets us do something that is really awesome, which is lie about physics a bit. Ignore the edges of an object where things aren't tidy and neat. So, infinite line of charge. That's our next practice. Now, the thing about an infinite line of charge is, what do you think the electric field would look like around an infinite line of charge? First, looking at it the way I've drawn it here, can we all kind of agree that the electric field, at least in those two dimensions, must be kind of perpendicular to the line? Now, you did a bar of charge, and you know that when you got to the edge of the bar, it started to lean outwards, but there is no edge to this bar. So no matter where I am, wouldn't you agree the line of charge produces an electric field that is perpendicular to the line? Trying to make a reasonable argument, because this is what I need you to be able to do. Now, if I was to turn the bar on its edge so it's looking at me, of course that would mean it'd be going through me because it's infinite. Would you also be able to agree that the electric field would be kind of like that? Can everybody agree with that too? So that we have bits of that electric field coming out of the board, bits of it going into the board, because it's all around that line. I need us to have both of these concepts in mind. We're going to use Gauss's law to derive an expression for the electric field around an infinite line of charge. So I need to come up with a surface that I think I can wrap around this that has good exploitable symmetry, but also could be used to determine the electric field. So, it might not be obvious what to use, but I think some of you can probably recognize that, at least over here, I'd probably want something circular. But I can't make it infinite, because it has to be a finite shape. So when I'm thinking about it over here, I'm thinking perhaps a cylinder. Like so. And I'm trying to set the cylinder up so that it has a top and a bottom. So this is the top, and thus the bottom. I'm trying to set up the top and the bottom so they are perpendicular to the infinite line. Gauss's law said I had to use a closed and bounded surface, but it didn't say it had to be smooth. So what I've really done is I've suggested that there are three surfaces that I can bring together that are a closed and bounded surface. There's the side of the can, and the top and the bottom of the can. Together, they form a bounded and closed surface. Questions at this point? So, I have a set of steps. I want to calculate the flux first. Now, this is a sum. And because of the dot product, it is a plain old algebra sum with no direction. There's nothing that stops us from breaking this up into pieces with separate sums for each surface, as long as each of the pieces together form an entire surface. Notice my integral no longer has the loop on it because each one is a piece. And I'm going to say that this is the side, this is the top, and this is the bottom. And as long as I do all of those integrals, I will have the entire flux. We good to go? Now, top and bottom are pretty easy. I mean, I don't know what the electric field is. I don't know what E is at all. But I do know that is there any electric field that pierces the top or the bottom? I mean, do you realize I drew it perfectly so that it's perpendicular to the line of charge? So if I looked at the direction of the area here, that's dA for the top. And the electric field right there would have to be 90 degrees from the direction of the area. So what would the cosine have to be here? It'd be the cosine of what? 90 degrees, right? Regardless of the fact that the electric field is probably changing all along that length, I'm going to be multiplying by the cosine of 90 degrees, which is going to make this whole thing 0. There is no flux through the top. Just like there's no flux through the bottom. I'm exploiting the symmetry in order to focus me on the sides. That's why I had to make my Gaussian surface just right. If I had chosen a different surface, this wouldn't have worked. If I had tilted my surface, it wouldn't have worked. I'm trying to be careful and make sure my surface is concentric with the line so that there's no electric flux. There's no electric field that pierces the top or the bottom. Which leaves me with just considering the side, which is pretty straightforward now. Because the side's going to have an electric field that is in this direction and an area that is in the same direction. And that would be true no matter where I look. And would you agree that if the side is the same distance from the line, it's likely that the electric field is the same value? Because if we can agree on that, then I can get rid of the dot product and everything and pull the E out front. Oh, you know, the hot breakfast discussion is the exact amount of time I need. What is the area of the side of a cylinder? That's right, 2 pi r times the height. That's the height. Now I want to finish, but I know some of you need to go to lunch and all that. But consider this evening, how much charge is enclosed? Like how much of the actual piece of charge is enclosed? Go ahead, Abigail. We're not there. We need 10 more minutes. Well, think on that tonight, and we'll talk tomorrow.